Welcome back. Today, we're going to look at the operating system side of virtual memory management. We'll look at how paging is implemented, some of the policy decisions that we can make, and how do we deal with memory resource management in general to make a better use of the hardware. Then we'll see the user level side and how applications interact with the operating system to request memory or to notify the operating system of its memory usage patterns. And then leave off with a more detailed view and a case study of the 4.4 BSD virtual memory system. This is based on Mach, and it's pretty representative of most modern operating systems. Let's look at the operating system's workflow for paging memory in and out. Here, we're assuming on the left that a program just loaded some memory address. The reference in the processor attempts to look up in the page tables to see if the memory exists. And as we see in the diagram, the memory is marked invalid. This will lead to a trap giving the operating system control in step 2. In step 3, the operating system realizes the memory is somewhere on disk, so it'll allocate a page and read that memory from disk. Once it's brought the memory in, it can then go ahead and update the page tables, inserting the reference to the correct page, and restart that load instruction that caused the exception, the page fault exception, in the first place. This basic strategy allows us to use more memory than is present physically on a machine, because we can move memory back and forth to disk or to an SSD to make use of that resource. In some OSs, there are even alternatives to this, like memory compression, which is used in Windows, Mac OS, and some hypervisors as an alternative way to swapping. While the mechanism itself is fairly straightforward, the problem really comes down to the policy decisions that you make when implementing memory management. The main problem is that a disk or even an SSD is going to be much slower than memory. Because of this, there's going to be a lot of costs associated with taking the exception and reading and writing data to and from disk in order to service paging requests. So the way that we address this, and was roughly using the 80-20 rule that I mentioned last time, what it says is that roughly 20% of memory gets about 80% of the accesses. The remaining 80% of memory is getting a small amount of accesses, roughly the remaining 20. So if we see in this diagram here, we can see that we have these hot regions that represent a small fraction of memory, roughly 20%. And the remaining smaller bars make up the majority of memory, but are relatively cold. They're accessed infrequently. So what we'd like is we want a policy where we place the hot pages in memory and the cold pages on disk and only bring the cold pages in as needed. So this brings us to the main challenges of paging. The first is that we need to be able to resume a process after a fault. So we saw this a little bit when we talked about exceptions last time, and we'll see a little more detail specific to faulting today. And the second is, what are the pages that we want to fetch from disk when we do get a page fault? And what are the pages that we're going to evict or eject when we're running out of memory? So how can we restart instructions on the MIPS architecture? This is all going to be architecture dependent, but roughly the structure is going to be the same across all computer architectures. The hardware is going to provide us with just enough information to ensure that we can restart an instruction that caused a page fault exception. We receive the faulting virtual address, as we mentioned in the exception lecture, in coprocessor 0's vAddr register, and the faulting instruction address is in coprocessor 0's EPC register. And this is going to also have trap information about whether it was a read or write or what caused it, with the type of trap and the other flags specified in the coprocessor registers. With this information, we can allow the processor to allow us to resume the instruction that caused the fault once we've serviced the page fault. And we do this by essentially using that return from exception instruction that allows us to return back to the application and continue executing. One of the nice properties is that, especially for these simple load and store instructions as they are presented on MIPS, it's very easy to restart the instruction. The exception occurs before the instruction completed, and we'll just re-execute the instruction to allow it to complete with the new memory address loaded. So let's look at a few more complicated questions that we'll spend quite a bit of today's lecture on. How do we decide what to fetch? So we've seen a page fault, we've received a page fault from the application. Well, it turns out when you take a page fault on most disks and even on most SSDs, asking for one page or 2 pages from a disk or an SSD doesn't significantly change the performance cost of that operation. For small IOs, typically the overhead from 1 or 2 or a couple blocks is essentially constant. It's more the overhead of the controllers and communicating with the device and back. So because of this, most OSs will choose to prefetch some number of pages, assuming they see an access pattern that deserves that. We'll see later when we talk about the user space API, there's an madvise call in some operating systems that allows you to tell the operating system whether or not you're going to access things sequentially or randomly to turn on and off prefetching. Also, the operating system may attempt to detect a prefetch pattern that works by seeing whether or not access patterns appear to be sequential or not. The other thing that we can do is that we can also play some other tricks with the operating system here, where we'll pre-zero unused pages. And this is, interestingly enough, done usually while your computer's idle. When your computer's not being used, we start zero filling pages lazily, and we only zero them on demand during page faults. This is another source of page faults that I should point out. So here's the more interesting question, is how do we select which physical pages to evict or to eject? And we'll see in a couple slides a little more detail about different eviction policies and how this can be done. But basically the problem comes down that we need to look through all of the memory of an application and find some pages that we believe are cold or idle, and then take those pages and swap them out. And there's multiple problems that can occur with this. It might affect caching behavior. It might affect also how we deal with page tables. So as an example, if you remember last time, I did point out how MIPS and even x86 have multiple page sizes. x86 had the 4 kilobyte page and the option for a 4 megabyte page. And MIPS, or in this example, Alpha, has many different page sizes that can be supported. This is great because we can reduce the pressure on the TLB. These are generally called super pages. In order to reduce the overhead of the TLB, we'd like to use these super pages as frequently as possible, but it means that swapping out decisions are going to be made at a coarser granularity. So there's different ways that this can be dealt with. The paper that I cite here shows one of the nice techniques doing this, where we can actually have pages that we are super pages, break them up as smaller pages in the TLB temporarily to look for access patterns to determine whether it's worth breaking a super page or not, and making more complicated decisions based on the usage pattern that we see in the page tables or in the TLB. So now let's start with a simple strawman policy of a first in, first out eviction policy to see how the eviction is going to work in this system. So here we have a string, which is going to be a sequence of pages that we're going to access. Imagine that our process just has 5 pages of memory, and our computer only has 3 pages that we can allocate to the process. And we're going to access the pages in this order. And what we can see is if we have these 3 physical pages, and we evict the oldest fetch page first, we can see the access pattern That's going to result in how many faults required to run this program. So we first load in 1, 2, and 3 as the first 3 pages as we start executing. So we take 3 faults to load in the beginning of memory. We then access page 4, which isn't currently in memory, and we only have 3 pages, so we'll have to evict 1 and take a fault to access 4. Now we see that we access 1 again, which results also in a fault because 1 had just been evicted to make room for 4. 2, similarly, is already been evicted to make room for 1 again, so 2 triggers a fault. And 5 we've never seen before, and we only have these 3 pages in memory, so we have to evict 4 in order to make room for 5. And then the program accesses page 1 and 2. Pages 1 and 2 are already in memory, so they won't lead to evictions, but then 3 and 4 will, and the remaining page 5 won't. So what we can see here is that we had 9 page faults when we accessed this access pattern with 3 pages of physical memory. Here's where it gets weird. When we have 4 pages of physical memory and you run the same access pattern, and you can try this on your own, you'll see that there are going to be 10 page faults. It's kind of strange. We have more memory, but we're using it in a worse way because of the eviction policy. This is why selecting a good eviction policy matters. Some applications even have customized eviction policies where they take control of the eviction because they understand more about their own workloads. This is common with database systems, for example, that know that they're going to access lots of memory. They understand ahead of time the access pattern based on the requests that users are making, and so they can make better use of an eviction policy. But for most applications, the general OS policy is going to be applied, and we'll see a few options today of how this is done. Having more memory doesn't always translate to fewer page faults, is known as Belady's anomaly. So we can see here, while the general trend is a decreasing curve where the more memory we have, it should reduce the number of faults, this isn't true in an absolute sense. As we can see, the change from 3 to 4 resulted in an increase because of the access pattern and the eviction policy. This begs the question, what is the optimal page replacement policy? Assuming that we know the access pattern and we know the future of what the workload's going to do, we could select the right replacements to make to minimize the number of faults. In the case I showed before, when we have 4 physical pages, we can get it down to just 6 faults, the first 4 pages, and replace only 2 pages additionally during the course of the execution. This isn't really practical, so we need a better alternative. So LRU is the most commonly used replacement policy. LRU approximates optimal through this least recently used policy. And the reason is that most of the time we find that the past is going to help us predict the future. So if we've seen pages been reused recently, they're more likely to be reused again. There are a few variations of LRU which we might touch on later in the term, like ARC, which is a variation of this. But generally for memory, we're approximating something similar to LRU. In the same access pattern with the same 4 physical pages, LRU does a little worse than optimal, and it achieves only 8 page faults. What's the worst case though for LRU? Well, the worst case is if you just have a linear scan of memory. If I linearly scan 5 pages of memory and I use least recently used as my page replacement policy, I'm always going to be faulting on the next page. But for most workloads, there's some locality which LRU is going to be able to take advantage and really reduce the number of total page faults in the system. The next challenge is to consider, how can we implement LRU? So these page replacement policies are used in all kinds of caching behavior, from disks to hardware and so forth. In the case of memory, this is challenging because memory accesses are incredibly fast. we don't have an easy way to interpose on every access to memory to visualize and understand the access pattern and generate an LRU list of pages. This would be too costly for any system to implement. So, could we do something to reduce this? Let's say we just time-stamped page tables. We modified the hardware and we got the CPU to timestamp every page table entry or every TLB entry. Well, every time you access memory, you're going to potentially have to update the page table entry. You can't just do it the first time that it's accessed. This is actually on every access. You'll have to constantly be updating these timers. You'll then have to sort all of the pages, and we'll see that just the timestamps themselves generates almost double the memory traffic. The sorting and processing that's going to have to be done is going to also be fairly costly on top. If we could do this, we could keep some kind of doubly linked list of pages and keep trying to resort them, but this is expensive, as I mentioned. So what can we do to approximate LRU? So we can't even get LRU on a memory eviction policy because of the sheer cost. So we want to be able to approximate it. So this brings us to the clock algorithm. Clock is a collection of algorithms. There's a few variations of clock that are used to approximate LRU. And the way the clock works is that it linearly scans over all pages in the page table, and generally speaking, it's going to scan for the access bit that we said is in the page table. The access bit will tell us whether the page was accessed recently, and the clock algorithm is going to reset that bit so that it can periodically check whether or not it's been accessed recently. So what happens in the clock algorithm is that it looks like a clock. So you can see in the diagram here, the hand is pointing to this page that's green, A equals 0, meaning the page has not been accessed. As the clock algorithm scans, it's going to reset the access bit on every page, and if it scans a page whose access bit is already 0, meaning that it hasn't been accessed since the last iteration of the scan, then it can choose that as a page to evict. This is known as a second chance replacement, meaning that the page gets a chance as long as it's been accessed in the last scan of the page table. Once it's made an entire circle through all the pages in your system, then it's going to decide to evict pages that haven't been used. The problem with clock, at least the way that I currently described it, is that memory tends to be very large. Because of that, the amount of time it takes me to scan over all the pages in the page table to decide whether or not to evict one will be very long. The second problem relating to that issue is that if we wanted to try to do that at a reasonable pace, we would have to incur a lot of CPU overhead. Remember that the operating system gets control of the CPU for a period of time, and it's going to implement the clock algorithm in software. So how can we deal with this? So this brings us to the first main modification that we'll do to this clock algorithm. And the basic one is that clock will have two hands. One hand is clearing the access bit, and the second hand is deciding whether or not to evict a page. So the first hand we can see here in this example clears the access bit, and the second hand at the same time in lockstep is making forward progress, and it sees pages that have been recently accessed and it'll skip them. And once it reaches a page that hasn't been accessed since the first hand cleared the access bit, it'll choose to evict that page. This will allow us to effectively shorten the time it takes to scan because we're using the distance between the hands as really our scanning interval. There are a few other variations of clock that can be applied in terms of policy and also in terms of implementation. One common one is that we also consider the dirty bit. Pages that are dirty means that those pages need to be swapped out. They need to be placed on a disk before they can be freed, versus pages that are cleaned don't need to be swapped out. They can simply be discarded and retrieved from previous swap or wherever their original source is. So in general, the OSs want to reduce the cost of not avoiding that swap out operation. So they'll try to consider clean pages over dirty pages for eviction. This is another way where we can reduce that overhead. Remember that in the swap path, if memory is already full and I need to bring in another page of memory, I'm going to have to discard one of the pages. It's easier to discard the page than write the page out to disk if we know it's already on disk. The second variation that we commonly see is that we can generalize swap to multiple bits. So instead of just one bit deciding whether or not it's accessed or not, we can have an n-bit counter that we generate as we're sweeping over the pages. And then we can evict pages that have only the lowest counts. This way we can have a gradient of heat telling us how hot or cold a page is rather than just simply a binary value. There are a lot of other replacement algorithms that can be done. We'll just mention a few common ones here. One is a completely random eviction policy. This is really simple to implement. We don't need to scan, we don't need to do anything, there's less overhead. And it's actually not terrible when we consider it avoids a lot of pathological cases. And this policy actually has some important applications. So we cite Walsberger's paper, a colleague of mine from VMware, who developed used this algorithm to avoid double swap. The problem in virtualization and hypervisors in general is that when we're making swapping decisions at the hypervisor level, remember that the operating system is also making a swapping decision. If both of them are using clock, they're likely to choose the same pages to swap out. The hypervisor might swap a page out, and then the OS decides to swap the same page. What's going to happen? Well, the OS is going to try to take that page and write it out to disk, requiring the hypervisor to swap it in and then have the OS swap it out on behalf. So the paper discusses a few ways that virtualization tries to avoid double swap. One is by using random eviction when there's no other choice. And two is by artificially inducing memory pressure inside the guest OS to force the guest to make swapping decisions on behalf of the hypervisor. If you have time, this is a really great paper to read to understand some of the resource management problems in virtual memory. Two other eviction algorithms that aren't frequently used, but they have some applications, are least frequently used and most frequently used replacement algorithms. And lastly, we have workload-specific policies. And the most common and good example we can think of for this is database systems. Database systems, when you make a very large complex query, you're doing a join on a table or some other request that requires accessing a large amount of a database, the database understands the workload and the access pattern perfectly. It makes a plan and it's able to even change its behavior based on the resources available in the system. This means that the database can make the optimal decision of choosing the right algorithm combined with the right replacement policy to minimize the cost of a database query. So if you go on to look at database systems courses in your fourth year, they'll cover some of these topics on how databases can do this. And then this is one of these cases where the application just has so much more information than the operating system. Let's look at this naive paging diagram to look at another issue with paging. Here, we've taken a page fault and we need to fault in a page. But if we're under memory pressure and all the pages are currently in use, what are we going to have to do? Well, we'll have to find a victim page using our page replacement policy, swap it out to disk to make room for the page that we want to swap in. And we'll have to wait for that swap out to complete before swapping in the subsequent page. This requires us to do 2 disk IOs per page fault. We'll see this more when we get to the storage lectures in a couple of lectures, but the problem here is that on a traditional spinning disk, we really should only expect about 100 to 200 disk IOs per second. Remember that old traditional spinning disks are mechanical devices, and if there's a random IO pattern, which is common for a swap device, then what we'll see is that we're going to have to physically move this disk head as we're reading for each IO. A common solution to this problem is page buffering. The idea of page buffering is to reduce the number of IOs that are in the critical path. So generally, when you incur a page fault, you'll just do a single IO to read the page in. And we do this by just keeping a pool of free pages around. When we take a fault, we'll just grab one of these free pages and page in the fault page that was requested. There are a few ways that this is done. One is often to integrate the memory allocator and the eviction and page replacement policy code together. This allows the OS to find victim pages, place them in a victim pool that can then be taken for allocation, or if a process faults on them, in the meantime, they'll be given back to the process containing the data ready to go. A second consideration is whether or not the page allocation decisions are done locally or globally. A global allocation scheme doesn't consider the page ownership. It doesn't consider whether one user or one process needs more memory than the other. So imagine if you had two processes and one of them is just looping through a giant array larger than the size of memory. Well, all the page faults in it might make a global allocation scheme allocate more memory to that process. A local scheme, on the other hand, will isolate processes or users, separately determining how much memory each one should use. And often there'll be some kind of two-level scheduling going on where a memory allocator is going to make decisions of resource allocation between users or between processes in these local schemes. One last problem we're going to consider with paging is the idea of thrashing. Thrashing is when an application is constantly swapping in and out of pages, preventing it from making any forward progress at a reasonable rate. Assume the application far exceeds memory and just accesses one integer on every page. What's going to happen? If the application uses just a simple linear scan of memory, it's going to constantly be page faulting on different pages, waiting for those faults, and then in the next instruction or a couple instructions later, take another page fault. We'll see that we're spending all our time doing I/O and almost no time using the CPU. What we really want is that we want virtual memory to be the size of the disk with the access speed of physical memory, but when we're seeing thrashing, we're getting the opposite. We're getting memory with the access time of disk. Thrashing can be a common performance problem when there's something wrong with our workload or the configuration of our hardware and software. One of the first reasons is that a workload doesn't exhibit any kind of temporal locality. There could be many reasons for this. Maybe the arrangement of data in memory doesn't make for good locality, and this could just be fixed through some application work. Or maybe the workload simply has no locality. It's truly a random access pattern. A second is that the hot portion of memory doesn't fit in physical memory. So imagine the 80-20 rule is still held true, but the hot portion of the application, the pages that are frequently accessed, exceed the size of memory. The 20% is far larger than the size of memory. And a third is that while each of the processes might fit individually, there might be too many for the system. There are a couple of ways that we can deal with thrashing. The first is to look at the working set and try to understand what's going on with the application. We could see whether or not the system needs more memory. Maybe simply we can't fit this many processes in the system, or we can't fit that single process even within the system because it needs more memory to satisfy the hot portion of the working set. Another approach is to look at the page fault frequency And we can consider that the page fault frequency is the page faults versus the instructions executed. Think of it in my example that I outlined earlier. If we're taking a page fault on every instruction or every couple instructions, then we're not really making any work. So the page fault frequency allows us to measure this and tell us whether or not we're actually making progress in an application. And as the page fault frequency rises, we could give more memory to the application. And as it falls, we could take memory away and possibly give it to other applications. And the last thing is also to look at the workload over time. The working set of the application is not constant. Depending at the granularity that we look at in terms of size and in terms of time, we're going to see that the working set is changing all the time. And there's going to be some spikes on this working set during the transition phases when we stop using one set of memory pages and we start using a different set of pages for the computation. If you recall in the last lecture, I showed a view of what an OS 161 application looked like inside of virtual memory. Here, I'm showing a more generic view of a process. Somewhere in low memory, we'll find the code, the read-only data, the initialized data, uninitialized data, and the heap. And finally, at the top of memory, we'll have the kernel, and somewhere below that, the stack that's growing down. Remember that the stack is part of the application memory. The heap is something that we'll get to more in the subsequent lectures. The heap is used to allow us to allocate small pieces of memory that can be used by the application. When you call malloc or free to allocate or free small fragments of memory, you're allocating them inside the heap. The heap has been implemented in different ways, and we'll see the two main APIs right now. The first is this use of this idea of a breakpoint. The breakpoint is just the address of the top of the heap. And there were two ways you could update the breakpoint. There's the break system call that allows you to say that all of memory up until this address should be allocated to the application, and sbreak that allows you to increment the size of the breakpoint address. You can use these to implement malloc, and it's a little bit harder in this case to implement free without somehow waiting for all the memory, the relevant memory above, to be released before we can give it back to the OS. But every time you want to malloc some region of memory to put some structure or to instantiate an object, also remember that if you're using C++, when you call new, under the hood, new is calling malloc. When you want to actually call malloc, you could simply implement it by calling sbreak and allocating some memory. It'll return the start of that address and allow you to really use that as the address for the object. Modern systems have improved this API and provide a lot more flexibility than early operating systems. And they introduced this idea of having many memory mapped regions. So here in this diagram, I show two memory map regions. They can be at arbitrary addresses. Like we saw in the OS 161 program example from last lecture, the process space can be sparse with various memory mapped regions representing files or arbitrary memory used by the heap and stack. The main call is simply called Mmap. Mmap is this sort of universal call that allows you to memory map a file or an anonymous region of memory. You can see that there are several arguments that are optional, including fd that allows you to pass in a file descriptor that you want to map in. If you pass in fd, you can then pass in an offset for it. Also an address that allows you to ask the operating system to map this memory region at a specific virtual address. If you give a null address, the kernel is going to select one for you. A set of protection bits that allow you to decide whether or not this region should be executable, readable, writable, or none. And finally, some flags that help the mmap call determine what you're actually trying to do. If you call it with map anonymous, it means that you're trying to map some arbitrary region of memory for the heap, and your file descriptor should be -1. Mapping something private or shared, decide whether or not those modifications are private to this process or going to be shared between multiple processes. In addition, there's a few additional calls that allow you to make other changes to the memory. munmap that allows you to unmap the memory, and protect that lets you update those protection flags. You could take a writable region and make it read-only or make it executable. msync that allows you to tell the operating system to flush all of the changes to the memory region back to the file. So if it's a file that you've mapped into memory, you can use msync to save that file back to disk. And also mincore, which allows you to identify which memory is actually in memory and which memory is been swapped out or not currently mapped. And some operating systems also have madvise. Madvise allows you to tell the operating system about the access pattern and other hints of what you plan to do with the memory. Most operating systems, including Windows and Unix systems, essentially are going to follow a similar pattern for their virtual memory subsystem to the one that we're going to describe now. We're going to use the 4.4 BSD virtual memory system as the one that we show off in lecture. This is actually originally based on the mock virtual memory system, which I cite here. The virtual memory subsystem is split into two main parts, Pmap and vMap. Pmap manages the hardware interface. So in OS 161, this would be the code that's managing the TLB, and vMap manages the machine-independent representation of memory. vMap in this model consists of one or more objects. Each object consists of a contiguous mmapped region. So every time you call mmap to map a region of memory, that'll often correspond to a single object. Objects can be backed by files or shared between processes or just be anonymous memory. The Pmap is going to allow us to abstract away all of the hardware-related issues. It's going to deal with the TLB. If there's a TLB, often it deals with some kind of cache for the mappings. The general operation and the way that this works is that calls to mmap, munmap, and mprotect update the vmap. They update a set of objects in the kernel that describe the layout of the address space of a process. The vmap routines then call into the Pmap to invalidate various page mappings and to update the TLB if necessary. On a page fault, the exception handler calls into the VM Pmap to load into the TLB, and often there's going to be a little cache if there's a TLB that'll try to load from that cache. If it's not available, then it calls into the vmap code as the slower path to ask it to find the actual mapping. When there's low memory, the Pmap is really meant to be a cache. If it's using a lot of memory, often this is going to be discarded and can be recreated on demand through the vmap. This means that the vmap is the original source of truth. It describes memory. The VM Pmap is just trying to provide a set of abstractions to remove the detail of the hardware so that the operating system can run on multiple architectures. If we think about most OSs today, they often run on multiple architectures. If we think about most operating systems today, including Windows, Mac OS, and Linux, they're all running across multiple architectures, from phones to desktops and servers that are x86 and ARM and other architectures. So the 4.4 BSD VM system basically says that every process is described by a VM space. This is the address space, the abstract structure that represents the entire address space of the process. And it contains three main pieces: the vMap, the machine-independent view of virtual memory, the Pmap, the machine-dependent data structures for this computer architecture, and some statistics that are used for system calls like getR usage that return statistics back to the application. vMap is a linked list of vMap entry structures. Each vMap entry covers one of these contiguous regions of memory, and it points to a VM object that was created when we first called Mmap. A VM object is the source of the actual data. It says whether to read data from a file backed by a vnode, as we'll talk about when we look at file systems, for memory map files, or it points to a list of VM pages that represents all of the pages in memory. And these VM objects can actually become a chain that are used for copy and write semantics. So when you fork a process, what happens is that there's a VM object from the original process that's going to be shadowed by two other VM objects. The parent process and the child process will have their own VM object to have a private view of memory. They'll share underneath the base VM object. When they read, they can read from the base object if the page hasn't been modified. But as soon as they attempt to write to any memory that's existed prior to the fork call, that page will get duplicated and a private copy will be given to the parent and child. Those will be held by this shadow object. So let's look at a diagram to see how this structure works. Here we show on the left the VM space, the vMap, the Pmap, and the statistic structures. The vMap, as I mentioned, points to a bunch of vMap entries that then point to objects. The shadow objects being first, and then eventually backed by some kind of object underneath that's a vnode or an anonymous memory object. And that'll point to the VM pages that represent the actual data used by the process. The Pmap layer, as I mentioned, holds all of the architecture-specific virtual memory code. It deals with all the issues specific to that processor, to that architecture. The VM layer is going to invoke a set of calls, and if you look back at the mock VM paper, it defines a clean API, a set of calls between the Pmap code and the regular map code. Every time there's a page fault, it's going to try to install mappings. It's going to change protection whenever you're changing the protection bits or unmapping pages. We can call into the Pmap code to update those. Or if we need to query the dirty and access bits, again, we can call into the Pmap code to retrieve those dirty and access bits for our replacement algorithm. The Pmap layer is done lazily, and we can discard the mappings. We don't really need to tell the VM layer much. We just need to make sure that we propagate dirty and access bits, and then we can discard mappings and retrieve those mappings from the VM map at any time. Whenever a process faults, we'll then recreate the Pmap entries, whether they're through a TLB or through page tables in x86. We'll recreate them by querying the VM map. The Pmap also is going to handle a lot of the restrictions imposed by caching. So as I mentioned, there are a few ways that each entry can be used. A given vMap entry represents a given segment of memory or region of memory or mmapped segment in a process. You might have a read-only text segment that's backed by a single file object. So when you load a program for the first time in most OSs, we don't actually read all of the program's data in. We read the headers, and the operating system figures out just enough information to describe what memory should look like, and it creates a set of vMap entries that correspond to the text segment, the data segment, the stack, and anything else described by the program binary. So the text segment will be this read-only one, and that segment just basically describes the file object underneath. And as pages get faulted on, they'll actually be read in from disk. We can have a read-write data segment. The read-write data segment, we don't want to write those changes back to the binary, right? If your program has global variables, those are in the read-write data segment. You don't want, while you're running the program, to update and start modifying the binary's default values. Instead, you create a writable data segment. You have a shadow object that collects all the writes. So every time there's an attempt to modify one of these pages, we'll create a copy and store it in the VM shadow. The shadow object will collect all these modified versions of these pages, and pages that are read-only can then be retrieved just from the file object itself. And finally, a writable stack. The stack usually is not in your program binary. It's not described by the program binary. It's just determined by the operating system. And it's an anonymous object. It's not backed by a file. It's just backed by physical memory. As I mentioned in the earlier example, whenever an application forks, what are we doing? We're essentially duplicating the address space. We create a new address space, which is a new VM space and a bunch of Vmap entries. But we don't actually want to copy all the data of the program because that's really slow. So instead, what we're going to do is we're going to share all of the memory segments that we can. The text segment, the segment where the code is for a program binary, is read-only. So we can share that segment between the child and the parent process with no problem. The data segment, as we saw above, has a shadow region. All we'll do is create a new shadow region on top. So there'll be two shadows stacked on top. One for the parent, one for the child. And both the parent and child's shadow objects will point to the same shared shadow object underneath that previously existed prior to the fork. The stack, again, the same thing. It's an anonymous object. We'll create two shadow objects, one for the parent, one for the child, and all new writes will be collected as pages that get duplicated, and individual private copies are placed in each shadow object. Over time, as processes exit, whether it's the parent or child process exits, we need to discard these shadows because we're creating these long chains of shadows that retain memory. They retain all the pages that have been modified individually. So when we see that no other process is referencing a shadow, we can then collapse multiple shadows and sometimes even collapse shadows back into the original object. So imagine in my example, I had a program I called fork. The stack is an anonymous object and it has a single shadow. The child process exits. When it exits, no one else needs that shadow anymore. We can take the anonymous object of the original stack and the shadow of the parent and merge them back in or collapse them just to reduce the amount of extra memory laying around in the system. Let's think a little bit more in detail about how the page fault process works here. So we said that the page fault process starts in the Pmap code. We get a fault. It figures out that it doesn't have the memory, or maybe the permissions. Maybe you tried to write to read-only memory or to copy and write memory. So it calls in to the vMap code. The vMap code traverses the vMap entry list to find the appropriate entry, to see which entry represents the memory that we received the fault on. If there's no entry, then most likely the process has an invalid pointer, and usually this results in a seg fault and we kill the application. If there is, then what we'll do is we'll traverse all the shadow objects. We check at each shadow object level, is a page present that represents the specific address that we're asking for within this object. If it is, we can hand that page to the process, to the Pmap code, to have it mapped in and continue executing. And we'll scan each shadow object all the way until we get to the final backing object, whether it's a vnode or an anonymous memory object. The caveat here is if you're taking a writable fault on a page that's not on the top, on the first shadow. What this means is when you take a write fault and the page is marked copy and write, it means that the page was mapped in read-only because it was in a higher level of the shadow. The first shadow object is the only one that the process can write to. Anything after that, the second or third shadows, or the backing object after that, will be read-only. So when a write fault occurs, what we'll actually have to do is take the page, create a duplicate of the page, insert it into the shadow object so that there's a private copy of that page, and then map that new page as writable. And lastly, in some cases, if the page is just anonymous memory that's never been mapped, we also have to consider the case where it's never been mapped, it's never been used, and we'll just have to insert a brand new page, possibly zero filled, that we can give to the application. Hopefully the combination of last lecture and this lecture has given you a better understanding of the virtual memory hardware and software side, a look at some of the problems and how the operating system's trying to manage resources when you exceed the physical memory in the system, and a look at one implementation of virtual memory that should be representative for many operating systems out there.